Hello, this is the first video in fluid mechanics. It's going to be a little introduction, talk about units and dimensions, and talk about some fluid properties. So let's get to it. First thing you want to ask yourself is, what is a fluid? It's a good way to start. Well, you can use a lot of different things as a definition, but the easiest one that can be universally true is that a fluid cannot sustain a shear force. Okay, so let's look at this one on the left. Let's say this is a solid right here that we apply some kind of force to, and see that the bottom is fixed somehow. Well, it will deform to some amount, but will stop. That is, if it's a small force and a small displacement, right? And so it can withstand a shear. It can hold in place, and it can hold that shear. But if this thing is a liquid or a fluid, I should say, because gases are also fluids, if you apply a force to it, if you're able to apply some kind of force to it, it'll keep deforming. It'll keep moving. It'll flow, right? It can't sustain a shear force. Another way of looking at this, a good example that gets used a lot of times, is if you had a flat plate that was lying on top of a fluid, right? Let's say it's a liquid, right? And so here's the liquid right here inside the trap between this flat plate and the ground, right? And so you move and you pull this flat plate. So what you're doing is you're applying a shear force to some of this fluid. One of the assumptions that we make is that the molecule that's closest to the plate is going to stay attached to the plate, and the molecule closest to the ground is going to stay attached to the ground. So if this thing is moving, let's say it has some velocity v, this top molecule is going to have the same velocity as the plate, right? But this guy is going to stand firm. So at this, like a little time after having moved down this way, we get this velocity profile, as we like to say, and that right there is sort of the shear profile that's going on. And we take a look, and we will find later that this slope right here, based on the height and the amount of velocity that's going on, is actually going to be defined as viscosity, which is a fluid's resistance to flow. Right? It's resistance to shear, but it does resist a shear, but it doesn't sustain a shear. Okay, so a fluid can flow very slowly, but if it continues to flow because of the force, that makes it a fluid. And it could be liquids and gases, but it could also be something strange like a very, very viscous tar that might move really slow but it still will continue to move if a force is applied to it. There's other kinds of strange fluids, like non-Newtonian fluids. It could be plastics or of some sort, where if you put a force on it, it doesn't necessarily react like you would expect, like maybe water or air, but it's still a fluid. They have special properties to them I don't need to go into. But they could be kind of little strange. But these are generalities we're going to talk about, and it can't sustain a shear. That's the answer to that question if it ever comes up. Now, we're going to move on to dimensions, dimensional homogeneity, and units. All right? Well, first off, we want to make a distinction between units and dimensions. Units could be something like feet and inches, meters, millimeters. It could be pounds. It could be slugs, newtons, all those type of things. Those are units, okay, that you would apply. And you could have a system of units, British gravitational, or you could have system international, SI units. But when it comes to dimensions, we really want to try to get to the heart of what is going on in an equation, right? And we'll also use this thought process in many different ways, but also there's something called Buckingham Pi that we'll cover later in the semester, that we really need to be familiar with what the dimensions are of something. And also you'll find that a very useful tool in engineering is to check the dimensional homogeneity of an equation to really get an idea of what's going on in the equation, and just as a test of the thing. Okay, so first off, let's take a look at what we're really talking about. There's two systems that we could use for dimensions. That would be the FLT or the MLT system. And just like you could kind of guess from looking at this, the difference between them is the FLT system uses force and the MLT system uses mass. So, and they're maybe perhaps easier to understand in one setup than it is in the other. So, for instance, in something like force, well, it's easier, obviously, to use F. It's easier to use force. But in the MLT system, we're dealing with mass. We have mass, length, and t to the minus 2. Well, what is that? What is going on? What's the difference? Well, that's really F equals ma, right? If you take a look at acceleration, it makes sense that acceleration is going to be length per time squared, like meter per second squared or foot per second squared. So you can see that this is actually the go-between between these two systems if you wanted to do that, but it's also written out in a table that you could look. So you want to try to look through these. One that I want to highlight is energy. Force times length. It's force through a distance. It's a good one to remember. Or you have something like power, which is that energy per time right here, right? FL, so it's force through a distance per time. So that could be, and we can convert that into horsepower, or we convert that into a kilowatt, that type of thing. Other important ones are pressure, that we might have an FLT system, but looks quite different in the MLT system. So one example of the dimensional homogeneity that comes right out of your book is an equation right here that we say Q is equal to 0.61 times A times the square root of 2GH. Okay, and this will come up later in the semester, actually. But this is volumetric flow rate. Okay, so volume flow rate. So it's the same, but notice in either the FLT or the MLT. So that's L cubed T negative 1, right? So it could be feet cubed per second. It could be meters cubed per hour, what have you. And then we'll carry the 0.61. The reason why we're doing this, one amongst the reasons we're doing this, is we want to check the if there's anything buried within this coefficient. If there's maybe some kind of unit. If this is not dimensionally homogeneous, that means that the coefficient has within it some kind of units. And that's a good thing to know, because then we know that equation cannot be used in both SI or British gravitational. It's really, if it has units built into it, a coefficient does, that means that it's not like a universal equation. So this is another use for the thing to check. All right, so I'm going to pull the square root of 2 outside of that. And for A, that's going to be length squared. And right in here, acceleration, so that's going to be length time minus 2, right? And the h is another L, so I'll go ahead and put that in there. Is right, another L, so it's L squared, right? Because acceleration was L t to the negative 2 right here, right? And then we put L times that because the height was in there. So now underneath the square root, we have L squared t to the minus 2. We could take the square root of those, and it ends up being Lt to the minus 1, right? And we bring down that L2. We still have that coefficient 0.61 and square root of 2, and write it over here. And lo and behold, when we put those together, L cubed t minus 1 equals, then the 0.61 square root of 2, we have L cubed t minus 1. And we take a look and say, okay, it's dimensionally homogeneous. All right, so let me go down to the analysis of fluid behavior. This is really just a discussion and the breakdown of different kinds of fluids and what they mean and what they do. All right, so fluids can really be broken down into statics, fluid statics, and fluid dynamics, just like mechanics. Regular solid mechanics can be done. And fluid statics can be further broken down into compressible, that's gas, and generally gas, and incompressible, liquids. Now, and that means that for compressible, the density can change. And in incompressible, the density can't change. Now, there's a little bit of, fluids can be compressed a little bit, but generally speaking, they can't, right? So that's really a very useful thing in terms of hydraulics and that type of thing. Now, fluid dynamics can also be broken down into compressible flow and incompressible flow, and those could be described as aerodynamics and hydrodynamics. Very interesting. Now, fluid dynamics has a little complication that it can suffer from turbulent behavior, which can be a very nonlinear behavior, something that can be unexpected or difficult to quantify, but can be to some degree. And fluid mechanics uses many fundamental laws you've already encountered, including Newton's law of motion, so conservation of momentum, conservation of mass or continuity, and laws of thermodynamics, conservation of energy. That's a very important one, and something I wanted to go ahead and talk about, throw it underneath your nose for really quickly. And the conservation of energy really comes down into a very useful equation that I want to talk about really quickly because we're going to see it a bunch of times. And this is probably the most common way that it gets written. It says that if the density remains the same across something, that the pressure plus the velocity plus the weight pressure, that's the specific volume right there, times the height of the position at one point equals that of the other point. This is really an energy balance that says, hey, if there's a conservation of energy exists for something, that you can go between those 2 points and make this statement. There's lots of fluid behavior lots of things that we can learn about fluid mechanics just based on this one equation and various forms of it. This is Bernoulli's equation, very important. You should just take a note of it because it's going to come up over and over again. Now, in the measures of fluid mass and weight, this is an important thing to mention, the important property. The thing that we look at here is density, which has the MLT or FLT designation as ml to the minus 3. That is mass per volume. This is usually designated by rho, and it can have units of, let's say, kilograms per meters cubed or something like that, or maybe slugs per foot cubed, right? Or you can have specific weight. Now that's just taking gravity and multiplying it by the density, and that's usually given by the symbol. I'm going to call that gamma, I believe, and that usually has like newtons per meters cubed, or it can have pounds, and we'll call it pounds force per foot cubed, that type of thing. And now we can have this other thing called specific gravity. Now that's really just a ratio, and you'll see I've put it in here in the MLT system. It has zeros as all of the exponents. That's because it's a unitless parameter, right? A dimensionless parameter, I should say, but it's also unitless. And so really, if you're talking about water at a certain temperature, 4 degrees Celsius to 39 degrees Fahrenheit, the specific gravity, which is also usually just written as capital S, capital G, is going to be equal to 1 at that standard. Everything else is a ratio to water as a standard. So if you were to say that something had a density of some other fluid, let's say of tar or something, and we wanted to know what the specific gravity of tar was, we would take the density of that, we would divide it by water at, what did we say, 4 degrees Celsius. So that's what specific gravity is. And quite often, specific gravity is measured by way of using some kind of float, right? That's purposely like a little glass floaty thing right here. And you'll see that there's some, if this is the thing that we're going to measure, it could be like, say, salt water, for instance. If you want to know what the specific gravity of salt water is, you put this little thing in here, and there's like a little line, and it has, this glass will have little demarcations on there, and you line the thing up with your eye, and you see that, hey, that's what this thing will mark, what the specific gravity is. And it's a way to make an easy comparison of fluid density or a specific weight without care of units and based on a standard. So that's the end of the first video, and I hope I will have many more for you in the future. Goodbye.